Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, number of ways to arrive at destination. I will say for a medium problem, this is very difficult, probably more along the lines of a hard problem. I feel like this is harder than some of the hard problems that we've solved recently. But idea is we are given a connected, undirected graph, and each edge is going to be weighted, and the weight is going to be positive. What we want to do is two things, actually. We want to know what is the shortest path from 0 to n minus 1. We will be given n, so that will be easy. So we want not only the shortest path, but also we want to count how many of the shortest paths there actually are from 0 to n minus 1. So I think immediately when we see shortest path in a graph problem like this, we have to think of Dijkstra's algorithm. And thankfully, that actually is going to be the solution to this problem. The difficult thing is trying to augment Dijkstra's algorithm. Hopefully you have an understanding of it. If you don't, that's okay. But you definitely want to brush up on that. I'll try to be covering it in this video. But augmenting it to account for counting the different paths that also have the exact same weight, that's going to involve a couple extra data structures, but it's actually not as bad as you think. Like the final implementation, coming up with it is pretty difficult, I'm not gonna lie. So in this example, we see that there is one path from 0 to 6 over here that has a total sum of 7. There's another path here that has a total sum of 7. If we go down this side, we get here with a weight of 5, or a cost of 5, sorry. And then this path would have a total cost of 8. That's too big, that's not the minimum. But this path has a weight of 7, and I think this path does as well. So that's 4 total paths. This example can be a little bit misleading though. Let me show you one example that, quite frankly, I think makes this problem a lot easier. I always say that Leetcode oftentimes is about finding like the right examples. That is kind of a problem solving. So let me show you a very simple way to think about this problem here. We have our source node. We have our destination node. We want to count the paths that also happen to be the shortest. And they actually tell us in this problem, they sort of give us a hint by telling us this, that it could be a very large number. So we have to mod it by a prime number, which is going to be 10 to the power of 9 plus 7. So knowing that the count could be so big, it makes it obvious that a sort of brute force solution where we go through every possible path is not going to work, because that's going to be exponential. And if you don't believe me, let me prove it to you with this drawing over here. Imagine that on my first level, I have 4 nodes. You could think of this as like I'm making a little neural network or something. Almost like a perceptron from like machine learning, but I think here we have like one input and one output. But anyways, so imagine we have 4 different choices in the first step. And to make it even more simple, imagine all of these have the exact same weight of 1. So they're all the shortest. We know that generally Dijkstra's algorithm, it's greedy. It uses a minimum heap and it pushes. So like if this is our origin and we say, okay, it took us a total cost of 0 to get here because we started here. Now I'm going to go through my first layer, sort of like in a BFS manner with this min heap. I'm going to pop this. That's the smallest. Then I'm going to go through the neighbors. I'm going to add each of the neighbors to the min heap with the total cost it takes to reach that node. So each of these takes a total cost of 1. So then when we pop from the min heap, clearly like they're all a tie. It doesn't matter which one we pop first. And now to make it more interesting, imagine the next level, we have 4 more nodes just like this. And now you might see where I'm going with this. From this guy, I'm going to draw an edge here and here and here and over here. Now the drawing is probably going to get messy at this point, but I'm going to do that for every single node. So just kind of assume that's the case, even if the drawing is pretty messy. And from here, same exact thing. Boom, 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 and boom. And yeah, this is not really making any sense at this point anymore. But for each of these nodes, we saw that there was one way to reach each of these nodes, right? From here, I can go there. Okay, but what about this node. There's 4 ways to reach this node because I can go here and there, or I can go here and there, or here and there, or here and there. And we could do that for every one of these nodes. So 4 ways to reach each of these. And now the next level, it's going to go exponential. You can see that. So yeah, I can't draw all of this, but again, imagine the weight of each of these edges is 1. So it's exponential. So for each of these nodes, it's going to be 16 different ways to reach it. And it could kind of keep going like that. So this is kind of one of the worst cases. And I'm using this example to really illustrate the fact that this is going to grow exponentially. So with Dijkstra's algorithm, the overall time complexity is generally the number of vertices plus the number of edges multiplied by the number of vertices. So in this example, every single path to the last node is going to be valid. Every path is the shortest. I intentionally made the weights that way. So now you can see, as I'm adding 4 nodes each time, 4 nodes here, 4 nodes here, 4 nodes here, the number of ways to actually reach the final node is growing by a factor of 4. So compare these two math formulas. If I have 4 plus 4 plus 4, that's growing pretty slowly. But if I have 4 times 4 times 4 times 4, that's growing pretty quickly. Comparing 4n with 4 to the power of n, obviously this grows so much more quickly. So what's the solution to this problem over here? Because we can't just do a very naive Dijkstra's algorithm where we actually get every shortest path to the final node. We have to do sort of the sub-problems, which is to, I'm sure as you can imagine, rather than getting all 16 different paths to this node, and then, I mean, for this, it would be 64 different paths, because if there were 16 ways to go here, well, 16 paths, 16 paths, 16 paths, 16 paths, that's big. What if instead I just stored this number alongside that node and I said that, okay, there were 16 ways to reach here. I'm not actually going to go through all the different traversals of those 16 different ways. I'm just going to say that the shortest path to reach this guy, there were 16 different ways to do it, because for my previous guys, there was 4 ways here, 4 ways here, 4 ways here, and here. I'll add those numbers here. I'm not actually going to go through every path. And then I'll take those 16, add that, add that, add that, and get it there. So this way, it will be more efficient. I hope that that makes sense, that doing this in terms of sub-problems will make it more efficient, and it will maintain the general complexity of Dijkstra's algorithm, which is usually proportional to the size of the graph times log of roughly like the size of the graph. Okay, so once we know that, the problem becomes a lot easier. So we're going to have, along with our heap, I'm not going to draw the heap out. We're just going to use this picture to kind of refer to that, but we're going to keep track of the minimum cost associated to reach each node as we go. And along with that, we're going to keep track of the count to reach that node with the minimum cost. And I'm going to do a brief dry run now on this example to show you generally how it's going to work. Imagine we start at 0. We're going to say that the count to reach this node is going to be 1. That's kind of the base case, so I'll just map 0 to 1 down there. And then we're going to go through the 4 neighbors. And for each of them, we're going to say that the cost to reach each is going to be 1. So just to kind of simplify that over here, I'm just going to put like a little tuple. So 1, 2, 3, 4, map that to 1. And then for each of those, 1, 2, 3, 4, each of those is going to have a count of 1 as well. And then the way Dijkstra's algorithm is going to work, since all 4 of these have the same cost, we're going to just go one by one. We're going to pop this guy, and then we're going to end up adding all 4 of these to the min cost and to the count. We will say that the min cost for 5, 6, and 7, and 8 is going to be whatever the cost was to reach 1, which we know is 1, added with the current edge, which is 1. So the total cost to reach each of these nodes is going to be 2 if we take this node. And how many ways could we reach 5 from 1? Well, there was only one way to reach 1. We determined that over here. So we just take this count and add it to the count of 5, which hasn't been initialized yet in our hash map. So we will just set it to 1. So we can say for all of these nodes, not just 5, but 6 and 7 and 8, each of these has one way to reach it from 1. So we will put that down here. I will put 5, 6, 7, 8. and map it to 1. Then I'm going to go one by one. I visited this guy, now I'm going to do 2, and the exact same thing is going to happen. But right now for 2, we go through all 4 of these neighbors. We say that, okay, the cost to reach 2 was 1, and the edge weight of all of these 4 edges is also 1, so we do 1 plus 1 is 2. So we say that the cost to reach all 4 of these nodes is 2, but we already determined that in our hash map, so that's okay, it doesn't matter, so we are good. But what about the count? This is where it gets interesting. Well, from 2, there was one way to reach 2. So now we're going to add that 1 to each of these 4 nodes that we can reach. Well, they're already in the count hash map, so all we do is take this 1 and just add 1 to it. So it'll be 2 now. And the exact same thing, I'm sure you can imagine, is going to happen with 3 and with 4. So we're going to eventually get a count of 4 down here. And then finally, I'm sure you can imagine, we will pop each of these and say, okay, well, if there were 4 ways to reach this node, then there must be 4 ways to get to 9 from here. So in our count hash map, it's getting kind of messy. I'm gonna try to use this space over here. So 9 will be mapped to 4. Well, also with this guy, we're gonna get 4, and with this guy, we're gonna get 4 and there. So eventually this will end up being 16. There were 16 ways to reach 9, and the minimum cost to reach 9, like all of these were the minimum cost. That's what we also have to make sure of, because when we first looked at 5, we found that, okay, the cost to get to 5 was 2. We know that from over here. So the cost to get to 9 must be 2 plus 1. So it's 3. So in this hash map over here, we say 9 maps to a cost of 3. Let me put that over here. And so that's how it would work at the last step. We'd say, okay, 4 plus 4 plus 4 plus 4, because all of these are going to end up being the minimum cost 3. But consider this. Consider if it was a little bit different. Imagine if this guy, instead of being a 1, was actually a 2. Okay, how is that going to make things more interesting? To reach 8, it took a total cost of 2. So to reach 9, it's going to take a total cost of 2 plus 2. That's going to be 4. But 4 is actually greater than the minimum cost we already saw. So at that point, whatever contribution this was going to make, which it depends on the count of ways we could have reached this, which we know is 4, that contribution cannot be added to 9 in this hash map because those paths are not the minimum paths. We do not include any of those paths. So that's what would happen if we found a minimum cost that was actually greater. But what would happen if we found a minimum cost that was actually less? In this example, I don't think we're actually allowed to have a weights of 0, but for this example, I think it's fine. Let's imagine there was a 0 over here. So this is how this part of the solution would work. With 5, we'd say, okay, so far, this is the minimum cost, which is 3. So there are 4 ways to reach 5, so I add that over here. I get 4 ways. With 6, same thing. With 7, same thing. So with these 3, I counted 12 different paths to reach 9 that have a cost of 3. But now I see 8 over here. And for 8 to reach 9, it actually takes a cost of 2. 2 is less than the cost that we calculated originally. So, of course, we should update the minimum cost. This should be set to 2 now, and we should reset the count because we counted 12 paths. Well, it turned out those paths were not valid. They were not the minimum. We thought they were the minimum at first, but they turned out not to be. So now we reset the count and we say, okay, well, there were 4 ways to reach 8. So we will take 4 and then set it to that count over here. So rather than this being 12, it would be 4 in that case. So that's the general idea behind this problem. And what I talked about right now, where if we find maybe a path that has a greater cost, we ignore that. If we find a path that has a lower cost, well, then we update the cost and reset the count. That sort of part is not only going to be applied at the last step, it's actually also going to be applied like in the intermediate steps as well, because I'm sure you can imagine that over here, the same could have happened. Maybe there was actually a 0 over here. So it turns out all these other paths were too large. This was the only minimum path. Or vice versa, where maybe this has a weight of 2, so we would not include that path. Anyways, I think that's enough intuition. Let's go ahead and jump into the code now. So I will go ahead and reset this. And then the first thing we want to do, given like these inputs, is just build an adjacency list. Pretty easy to do that. I love using Python default dictionary, so I can just do this. Unpack the edges, unpack the time, which is basically the weight. I'm probably just going to use W because I don't really care about the context of the problem anymore. So doing this, we will map U to V. And it's undirected, so we can just copy and paste it in the other way. Next is going to be the Dijkstra's part. So I'm going to have a mod, which we're going to need a few times. And I'm going to initialize my data structures. The min heap is the straightforward part. I like to have a tuple. And what I like to do is, well, we have to put the cost first because we want the heap to be sorted based on the cost, but we're also going to include the node itself. So I'm going to do 0, 0 here. We know that the cost to reach the starting point is going to be 0. The starting point is also going to be 0. And then I'm going to have a couple data structures. I'm going to have a minimum cost array. I could also use a hash map, but in this problem with n, it's actually easier to just use an array. So that's what I'm going to do. And it's going to be initialized to infinity at each position. So this might be one of the first times I'm actually doing like a textbook Dijkstra's algorithm. For this problem is actually pretty necessary. But more than that, we also need the path count. This is like the variation of Dijkstra's algorithm. This is where we kind of diverge. So initially we can say that's 0 for everything, but we know that for the first node, the origin, it's actually going to be 1. So we're going to initialize that. It's kind of our base case. So now we say while the min heap is not empty, let's go ahead and pop from the min heap. We're going to get a couple values that we can unpack. The cost first and then the node after that. And now I'm going to go through every neighbor and neighbor cost. There's more I'm going to do like over here, but let's start with this. We're going to do the BFS part. We're going through every neighbor in the adjacency list of current node. And this is another part where we kind of diverge. So usually when I implement Dijkstra's, I just do like a visit hash set lookup here. And I also then do a visit hash set like insert here after we pop from the heap. Once we pop, we assume that that's the shortest path to that node. But this time I'm going to do it a little bit differently. I'm going to actually use the minimum cost to determine if we found the shortest path. So I'm going to say, okay, well, the cost to reach the neighbor is going to be the cost to reach the current node plus the neighbor's edge cost. So this plus that. Now, if this is less than the minimum cost that we have initially, which of course is infinity, for that neighbor, then we can say we found a new minimum. So new minimum cost for this neighbor is going to be the cost I computed up above. And the path count for this node has also been increased. So for the path count for this is going to be incremented, not necessarily by 1, but by the path count of the previous node. So we say path count of previous node. It's actually not going to be incremented. It's actually just going to be set to that, because if we found a new minimum, then we should be updating this. And we're not looking at the neighbor, we're getting the current node. And we can probably just assume that that number is like less than this large number because of the next step that I'm going to do. So we found a new shortest path to this neighbor. Let's also add it to the heap. Heap push to the min heap, this tuple with the new cost, neighbor or cost plus neighbor cost, and then the node neighbor. So that's one case. The other case, well, I guess there's two cases, right? One is obviously we found a new shortest path. The other could be like an else if where we just swap the direction of this, where we have like if the current cost is actually greater. Well, in that case, we actually don't need to do anything. So we don't need a case to handle that because it doesn't really matter if we found a new larger cost. We just skip that. But what about the other case, the other edge case where actually these are exactly equal? I changed this to equal. Well, that is the part where instead of resetting the count, we will actually increment the count. So here, I'm going to update this to taking the current value and adding to it the previous path count. And then this is the part where we do have to mod because we're potentially increasing the count. So mod this by the prime number. So this counting, this specific line of code, this is what's saving us the exponential time complexity, just so you know. rather than getting all however many paths there actually are, we're just treating it as a number. So we don't actually have to traverse that entire path. So there you go. And then at the end, I'm sure you can imagine what we're going to return, not the minimum cost, but the path count, and the path count for n minus 1. So this is the entire code. Let's give it a run. Okay, very sloppy mistakes. I really apologize for that. So first of all, here, we want to put the neighbor cost first, not the neighbor, because that's how we added it. So that's an easy thing to fix. But there's one more mistake that I made right at the beginning, actually. Well, in our adjacency list, we don't have a pair. We only add the neighbor. So let's actually add the weight as well. So just adding that W there and adding the W there first as well. So that should fix things. And for some reason, I called this path instead of path count. I'm not sure why I did that. I'm also not sure why that worked. But now let's run it. And finally, you can see that it does work and it is very efficient. If you found this helpful, check out Leetcode.io for a lot more. Thanks for watching, and I'll see you soon.